Welcome back to Upsc Study Academy, empowering aspirants and shaping futures. In the last video, we saw the topics about sound waves that included longitudinal waves, how sound is produced, the speed of sound in different mediums, and the characteristics of sound. In this video, we will be covering the rest of the topics on the chapter sound. Have you ever wondered how objects like bullets and rockets travel? This is called supersonic speed, which is defined as speed traveling faster than the speed of sound. But what exactly causes this thunderous clap that echoes across the sky when high-speed rockets and jets move? At its core, supersonic flight hinges on overcoming the sound barrier. This barrier represents the speed at which a flying object meets and matches the speed of sound, creating a shockwave. This intense resistance created by the air creates shockwaves, generating the iconic sonic boom. To achieve supersonic speeds, the aircraft must navigate through three critical phases: subsonic, transonic, and supersonic. During the subsonic phase, the aircraft operates below the speed of sound, building up momentum for the transonic transition. In the transonic phase, it encounters turbulent airflow and shockwave formation, requiring advanced aerodynamics and engine design to mitigate. And supersonic is when the aircraft takes off with the sonic boom. Race of sound and light. Sound and light are both forms of waves, but they travel at vastly different speeds. Sound waves are mechanical waves that require a medium, such as air or water, to travel through. They propagate relatively slowly compared to light, with a speed depending on the properties of the medium. Light, on the other hand, is an electromagnetic wave that can travel through a vacuum at an astonishing speed of approximately 299,792 kilometers per second, often referred to as the speed of light. This leads to the conclusion that light travels faster than sound. In rainy seasons, the flash of lightning is seen first, and the sound of thunder is heard a little later. This is due to the very high speed of light that we see the flash of lightning first, and it is due to comparatively low speed of sound that the thunder is heard a little bit later. Just like light waves, sound waves follow the fundamental laws of reflection when they encounter a surface. These laws dictate how sound waves behave upon striking a boundary. The laws of reflection state that when a sound wave encounters a smooth surface, such as a wall or a mirror, it reflects off the surface at an angle equal to the angle of incidence. Additionally, the incident sound wave, the reflected sound wave, and the normal, perpendicular, to the surface all lie in the same plane. The diagram demonstrates the law of reflection where the angle of incidence matches the angle of reflection, demonstrating the consistent behavior of sound waves when encountering boundaries. How does the stethoscope unlock the secrets of the human body? Let's delve into the stethoscope's workings, rooted in the principle of sound reflection. At its core, a stethoscope comprises of three essential components: the chest piece, tubing, and earpieces. When the chest piece is placed against the patient's skin, it captures subtle sound vibrations generated by the internal organs, such as the heart or lungs. These vibrations travel through the tubing by reflecting on the PVC material of the stethoscope tube and finally reaching the earpiece. This process allows healthcare professionals to discern subtle nuances in sound. Echo. Ever shout into an empty valley and hear your voice come back? That's like a nature-made echo. But did you know how? An echo refers to the reflection of sound waves off a surface, resulting in the perception of a repeated sound after the original sound has ceased. When sound waves encounter a solid object, such as a wall or a cliff, they bounce off the surface and return to the listener's ears with a delay. This delayed sound, often softer and sometimes altered in pitch or timbre, is perceived as an echo. The time delay between the original sound and its reflection depends on the distance between the source of the sound and the reflecting surface, as well as the speed of sound in the medium through which the sound waves travel. Echoes are commonly experienced in open outdoor spaces. Ever been in a big empty room and clapped your hands, hearing that cool, boing sound that seems to go on forever? That's like an echo, but it's called reverberation. Reverberation refers to the persistence of sound in an enclosed space after the original sound source has stopped emitting sound. These reflections blend together, creating a prolonged and gradually decaying sound that lingers in the environment. Reverberation is influenced by factors such as the size and shape of the enclosed space, the materials and surfaces present within the space, and the absorption and diffusion of sound waves by these surfaces. It is commonly experienced in large halls, churches, and theaters. Ever wondered how doctors can see inside the human body without using any incisions? What if I told you it's all thanks to a type of sound wave that's beyond the range of human hearing? Ultrasound, yes. Ultrasound waves are sound waves with frequencies higher than the upper limit of human hearing, typically above 20,000 Hz. These waves propagate through a medium, such as air, water, or tissue. Ultrasound waves are commonly used in medical imaging, industrial testing, and various scientific applications due to their ability to penetrate materials and produce detailed images about internal structures without causing harm or damage. But how does a machine create detailed images of our internal organs and tissues? Let's learn about the ultrasound, aka sonography machine. An ultrasound machine is a medical device that utilizes ultrasound technology to create real-time images of the inside of the body. It consists of a console with a computer and a transducer, which is a handheld device that emits high-frequency sound waves into the body and detects the echoes bouncing back. These sound waves, beyond the range of human hearing, penetrate through the skin and soft tissues, interacting with organs, blood vessels, and other structures. The echoes produced by these interactions are then processed by the machine's computer to generate detailed images of the internal anatomy in real time. Ultrasound testing for flaws in metals is a technique that utilizes ultrasound waves to detect and characterize internal and surface defects in metal components. A transducer emits high-frequency ultrasound waves into the metal component. These sound waves propagate through the material, traveling until they encounter a boundary between different materials or a flaw within the metal, such as a crack, void, inclusion, or discontinuity. When the sound waves encounter a flaw they are partially reflected back towards the transducer. The reflected waves carry information about the size, location, and nature of the flaw. The time it takes for the reflected waves to return to the transducer and the amplitude of the reflected waves are measured and analyzed. The signals received by the transducer are interpreted by a computerized system, which generates visual representations of the internal structure of the metal component. Ever wondered how submarines navigate the depths of the ocean without seeing what's ahead? Sonar, short for sound navigation and ranging, is a technology that uses sound waves to create detailed images of underwater environments and structures. A sonar system emits a series of high-frequency sound waves, typically inaudible to humans, into the water. These sound waves travel through the water as pulses of energy. When the sound waves encounter objects or structures underwater, they are partially reflected back towards the sonar system. The sonar system contains receivers that detect the reflected sound waves, or echoes, returning from the objects in the water. The time it takes for the sound waves to travel to the object and back, as well as the strength of the return signals, are measured. The detected echoes are processed by the sonar systems to create detailed images or maps of the underwater environment. The images represent the location, shape, size, and composition of objects and structures in the water column. Under the cover of night, bats take flight, navigating the darkness with precision. But how do they avoid obstacles and find their prey? Enters sonar. Sonar, which stands for Sound Navigation and Ranging, is a natural echolocation system used by bats and other animals to navigate and locate objects in their environment. Bats emit high-frequency sound waves, typically inaudible to humans, through their mouths or nostrils. These sound waves are emitted in pulses and act as a form of acoustic signal. The sound waves travel through the air and, upon encountering objects in the environment, such as prey or obstacles, they are partially reflected back towards the bat. Bats have highly sensitive ears that can detect and analyze the echoes produced by the reflected sound waves. By listening to the echoes, bats are able to determine the distance, direction, size, shape, and texture of objects in their surroundings, and thus they navigate with ease. Ever wondered how we're able to hear the world around us with such clarity and precision? It's all thanks to a remarkable organ that transforms vibrations into the sounds we perceive. But how? Let's dive right into the how. Our journey begins with the external ear, consisting of the pinna and the ear canal. The pinna, or auricle, acts like a funnel, collecting sound waves from the surrounding environment and directing them into the ear canal. The pinna helps us localize sounds and enhances our ability to detect the direction from which they're coming. Meanwhile, the ear canal, lined with specialized skin and wax-producing glands, protects the delicate structures of the middle and inner ear. Moving deeper, we encounter the middle ear, a small chamber located between the eardrum and the inner ear. Here, sound waves are transformed into mechanical vibrations. The eardrum, or tympanic membrane, acts as a barrier between the external and middle ear, vibrating in response to sound waves. These vibrations are then transmitted through three tiny bones called ossicles, the malleus, incus, and stapes, to the inner ear. The middle ear is connected to the back of the throat by a narrow tube called the eustachian tube. The eustachian tube helps equalize air pressure between the middle ear and the external environment, preventing discomfort or damage to the eardrum. It also serves to drain fluid that may accumulate in the middle ear, helping to maintain optimal hearing function. Finally, we arrive at the inner ear, a complex structure responsible for converting mechanical vibrations into electrical signals that the brain interprets as sound. At the heart of the inner ear we have the cochlea, a remarkable spiral-shaped organ resembling a snail shell. It's filled with fluid and lined with thousands of tiny hair cells, each sensitive to different frequencies of sound. When sound vibrations enter the cochlea through the auditory canal, they cause fluid inside the cochlea to ripple, stimulating these hair cells. This stimulation converts mechanical vibrations into electrical signals, which are then transmitted to the brain via the auditory nerve, allowing us to perceive sound. Next, we encounter the semicircular canals. These canals are crucial for maintaining balance and spatial orientation. When we move our head, fluid inside the semicircular canals moves as well, bending sensory hair cells located within. This movement sends signals to the brain, helping us detect rotational movements of the head and maintain equilibrium. Finally, we come to the vestibule. Within the vestibule, we find the utricle and saccule, specialized organs that detect linear acceleration and the orientation of the head with respect to gravity. Together with the semicircular canals, the vestibule plays a pivotal role in our ability to stand, walk, and maintain posture. And that's the end of this video. Thank you for watching UPSC Study Academy. Like, share, subscribe, and don't forget to hit that bell button.